So, our necessary Robert University from Vigilance.
Thank you. And that's the clicker?
Yep. Just give me 1 minute. Okay.
Cool. PhD student, University of Edinburgh, and under data. That job was being very involved in the university's plans that don't get it generating from like adversaries from feature level specifications. So background, so this is the image I think everyone's seen 100 times. And that neural networks people have talked about previously, they're adversarial examples. As you can see, there's always a disconnect between what we want a model to learn and what they are. So this is, I'm sure everyone's seen this picture before. It's very, very common that you have fully picture panda and your classifier suddenly says it's in small, which anyone looking at this would think, oh, that's still a picture of panda. And importantly, so in this work, we talk about cases where there's a disconnect between the feature space and the problem space and generating adversarial examples in that context. So in computer vision, the problem space is the actual image and the feature space pixel value. And those are kind of the same thing. Like maybe you have to round your pixel value slightly, but otherwise they're more or less identical. Whereas we looked at network intrusion detection systems, where that can't be said. They're a very natural target for adversarial examples. These are used to stop malicious actors from accessing your network. But so they're very natural target, but the problem space and the feature space are very, very far apart. The problem space is your network traffic, your PCAP files, or the raw network packets. And the feature space, typically in network intrusion detection, is some statistical flow summary. So instead of operating on packets directly, you operate on the statistical summary of an individual connection. And you say whether those are malicious or benign rather than the individual packets. So there is a prior attempts to overcome this gap in the network intrusion detection systems face problem space. Some try and enforce domain constraints on the flow statistics that you might generate with an adversarial example. And others operate directly on the network traffic. But the issue with these, former of these does not produce an actual network traffic that you can test afterwards. It just sort of says like, oh, here we've made some perturbations to our flow statistics that we believe are reasonable. You don't have a PCAP file yet. And the latter operating directly in network traffic, you do have a PCAP file at the end, but typically this is done by using a sort of a limited set of perturbations, allowable perturbations. So for instance, there's previous work that just manipulates the timing between packets. It doesn't manipulate the actual packets themselves. So then, or the contents of the packets. And so you have a limited set of transformations that you can make. If this works, well, there we go. And so, so we wanted to sort of overcome this gap between these things, and to do this, we didn't want to write like our own specification language for these specifications. So instead we turned to neural network verification. So verification is, a set of techniques that's quite often formally guarantee network behavior. So we can balance inputs and outputs in certain ways according to certain conditions and formally verify whether a neural network adheres to those. And typically these frameworks produce a counterexample if they don't adhere to those constraints. And so this counterexample is going to become the basis for our adversarial examples later. So your counterexample, it is a basic test. And to do this, we use Vehicle is a verification framework. It's high-level expressing specifications of neural network constraints. And so this is useful. We're taking this off the shelf. And importantly, so if you use a statistical adversarial example generation technique like PGD, you aren't actually guaranteed to find a counterexample or an adversarial example if it exists. It's a statistical approach, whereas vehicle-based sort of complete verification, so if there's an existing counterexample, if there's an existing adversarial example, it'll find it. So the methodology is using this tool, vehicle, off the shelf, and then we developed our own packet generation framework called PackGen. And I'm going to use that to generate our adversarial examples there, the PHAP. So PackGen is this specification-driven packet generation framework. It consists of 3 parts. First of all, given a PCAP file, there's a packet reader, which just reads these each individual packet in this PCAP file and tries to extract pertinent information that we're going to use to recreate packets later. And there's a chain builder. PackGen, the generation statistical model that we use is Markov chain. And so there's a step where we take information and then we sort of discard what we feel isn't necessary for recreating packets directly. And instead, we build a Markov chain tallying transitions between packets. And so the information, so each state stores information about each packet. Some of it is stored exactly, such as the packet flags of that packet. To prevent state flow, which is an issue with Markov chains, we don't use statistics about, say, timing. So we don't record the timing. We don't care about the timing differences between states. Instead, we just say sort of tally up mean transition time and the sort of standard deviation of transition times. So we discard a lot of information there. We only have a statistical approximation. And then finally, we have some packet writer that reverses the whole process. So given this Markov chain, it goes through it and can generate an actual PCAP file that you can open with Wireshark. And they show up with this Markov chain. So the point is that the Markov chain is sort of a compact representation that we can manipulate very easily to generate our adversarial examples later. So if we say it's more flexible, model and sort of intermediary model that we can manipulate later. So I'm going to do this then. So this is what we call the actual vehicle language looks. This is our specifications look like in the paper. And this is its vehicle is a sort of restricted subset of hostile. As hostile is pretty familiar. And so in this case, checking whether the model is robust to manipulating the packet size of the first packet in the flow. So it's a network package, they have some size, depending on how much information is being transmitted by the package. We're just saying, our specification here is our model robust to adversarial examples? If we let this packet size vary between 0 and h. And so we have this is what this change packets like function does, and then we say that like if the flow is malicious, we're taking anything malicious flow, and take all x if malicious flow is within these bounds, then that should still be advised as malicious. So this is our robustness constraint, and then we have a final property which we check for every single training input. And so if this were to produce a counterexample, this would look quite a lot like an adversarial example. So these are our specifications. And this is quite long. So so this is some packet data. You extract these features. This is now your feature space. You feed this into the model, and then we go over here. This could be used to model the features of the vehicle alongside specification. This produces counterexample, use this counterexample in packaging to generate the original packet data, and then we feed that through and we end up with a misclassification. So effectively, it's just completing this loop. We have some experiments to show this works. So in the first case, we're trying to show what packaging is a packet generation framework. So how good is it at doing that effectively? When we train packaging markup fields data, how well does it reconstruct your original training data in the first case? The first research question is when we've recorded that information exactly, such as packet sizes. And the second case is how well does it do when we don't record it exactly, which is in the case of this timing that we just use statistical. We look at various distributions of recreating sensible intervals on extreme packets. And we test this on the knowledge service data that we generated using different. And then we train PackGen on this data and we compare these distributions. So this should all just briefly say that knowledge service traffic is obviously very repetitive. It's, you're doing the same thing again and again and again, typically to a web server. Here's markup chain. It's relatively complicated. Like, it's not the exact same thing happening again and again. And so this just points that, this just to say that this example might sound trivial, but in fact it isn't, because there's things like random terminations of flows, things like that. It's actually more complicated structure than you think. And so the answers to our research questions basically, let's say, more information in the paper, but suffice to say, when you find yes, the PackGen does a good job of recreating our initial training data, and that if we look at the difference between the distributions using between our original training data and our generated data, we find that, like, yes, it does a good job using standard tests. So let's find online centers, find out and then for the inter-arrival times, which we don't record exactly, we find that certain distributions are pretty bad. So like the normal distribution, the uniform distribution for recreating inter-arrival times, they don't work. But we find that the gamma, using a gamma distribution, works to a level that we recreate the inter-arrival training data. Similarly, helpful flow durations are shifted slightly. Blue is for training data, packet data, the red is for training data, but it's overall works. It's similar. Then thirdly, we use this to produce adversarial examples with vehicles. So this vehicle produce basic counter flows. We write specifications according to certain threat models that we believe to be reasonable. So the three threat models are only manipulating packet sizes, only manipulating time sizes, and both, or only manipulating packet timings, and both these together. So we use input specifications that reflect those threat models and use them to query our network. Any counterexamples, we then use those to manipulate our markup chains in PackGen and generate a counterexample. That's like an actual PCAP file, importantly. So we find that does this work? And we find, like, yes, it does. PackGen works in the framework and works well in our vehicle. So we generate our adversarial. We compare vehicles to EGP, standard method of generating adversarial. And we consider a base network, and a more robust network, which we train adversarially. And we find that basically we get the exact same results as PTD in terms of adversarial accuracy, except for one case where vehicle provides a better attack. It finds counterexamples in more situations than PTD, which makes sense. It's a complete method. So that's sort of behavior that we accepted once. And then in every single case, we end up with traffic that of course specifications that is replayable. So we feed this all to package and we end up with a PCAP file at the end that like makes sense and can be replayed and tested in a full pipeline. And so that's basically it. To conclude, we've this so presented packaging, which we use in conjunction with vehicle to produce raw network traffic corresponding to a basic counterflow, counterexamples. Vehicle allows to write these domain constraints in a very readable form, and so the Markov chain is also a very readable approximation of your training data. There's some limitations to packaging. You can't just train it in arbitrary PCAP data. It needs to be inherently similar. And then vehicle, these verification frameworks are very slow. So we end up with a single adversarial attack, and it's much slower. And yeah, for future work, we want to investigate perturbations of like more complex feature sets. We use the very basic feature set. And that's it. Thank you very much.
Go ahead.
Thank you very much for the nice presentation. I have a question. If I understand correctly, which you use vehicle
Mhm.
for generating expenses that's offered on was wondering that what the model you consider for the vehicle. I mean, it's working the lack of cities or the one of cities.
So vehicle requires access to the model. Like you run a vehicle specification on the model itself. And so in order to generate these adversarial examples, you need access to the original model. So it's a white box attack. And specifically, so the threat model we'll consider is basically run these specifications these specifications in a way that only certain features can be manipulated by the attacker, which we find to be reasonable, to a reasonable extent. There's more detail in the paper, but basically we say the attacker can only manipulate forward packets, like packets originating from them. And we say they can only increase these features because it makes sense to pad packets and it makes sense to delay packets. But to say like, oh, I'm going to release this packet faster than your original benign original benign flow that you're basing this off of, that's not necessarily a reasonable assumption. And so the point is that vehicle allows us to express these things and more complex specifications using a pretty nice DSL. Compared to PGD, which would require, you can do it, but it's much awkward, sort of writing out feature bands individually and sort of these long feature bands to bound, whereas this is just far more readable.
Any other questions? Okay, a quick question that so you mentioned that your bank, yeah,
So what that is basically, again, more detail in the paper, but we have, so basically any anything that's like easy enough to represent in a Markov, in the state in the Markov chain, that can be sort of a target of an attack, if that makes sense. Yes. So yeah, so this is very much looking at this method. And basically, yeah, anything that you can easily represent in Markov like state transition or the state itself, then that sort of that's like a reasonable thing that an attacker can manipulate using PackGen and recreate the traffic and end up with like an actual PCAP file. So yeah, these are simple enough to start with, but you could say, for instance, if one of the features in your network is like the TCP options lane, that's something in our states that we represent. And so that could also be manipulated and generate corresponding traffic. Yeah.
So, my next question, so how long?
So right now is so right now we have like so it's very difficult to generate it, how should I put it? It basically depends on what you care about. So obviously like generation, so we focus on TCP traffic right now and saying that we're going to generate like completely perfect like TCP packets is a little bit far beyond what we're trying to but beyond what's like capable. However, we've chosen like sensible defaults such that you end up with like a PCAP file with minimal errors. Yeah. You see the old layers. Yeah. So you would see like you'd see things like there are many certain aspects of it that are more repetitive in real traffic because we're just using these defaults such that yeah. Yeah. But yeah, you're right.
Okay, that's
Thank you very much.